All right, welcome to our second Math Day talk. Before we start, I want to say thank you to our administrative assistant in the math department, Ricky. Is she around? She's helping out somewhere. Can we give her a round of applause, please? There she is. She's been vital in setting all of this up and making all of this happen, so thank you, Ricky. Dr. Darryl Nester earned his bachelor's degree in mathematics and computer science from Bluffton in 1988. After graduate work in statistics at Purdue University, he returned to Bluffton in 1992 to teach mathematics. His interests include probability puzzles, recreational math, differential equations, and developing web apps to demonstrate and explore mathematical concepts. So please welcome Dr. Nester.
All right. My mic should be like, yep, there it is. Okay. Thank you for coming this afternoon. I know it wasn't necessarily voluntary that you came this afternoon, but I appreciate you being here anyway. Title of my talk is Math Mysteries, Mazes, and Marbles, which mostly is just about having as many M's in a title as I possibly could. But this, I was asked to submit an abstract, so since I wrote an abstract, I had to include it in my talk. The brief version of what's the words that are up there right now is I really enjoy looking at problems that seem kind of mysterious or counterintuitive or almost have a magical component to them. And I was reminded of this quote from Arthur C. Clarke. I haven't read any of his works recently, but I read a lot of his stories growing up, and I remembered this quote from him that made me think about how when you look at something a little bit more carefully, something that initially seems magical or mysterious might not be so mysterious, so magical after all. So in that abstract, I said I was going to talk about two things, and one of them, the first one that I'll briefly talk about, and I'll postpone the explanation till the end, is mazes and mind reading. So this is some actual sort of magic, but like any magic, not real magic. But I need a volunteer from the audience. So can I get a volunteer? Someone who's, oh, and I should say, I know that 1 o'clock in the afternoon is like the worst time to be talking about anything, which means it's important that we move around and have some activity. So somebody want to stand up right now, maybe somebody who's starting to nod off a little bit and just come up here and be my mind reading subject. A volunteer somewhere. I see people being volunteered. Oh, okay, come on up here, come on up here. Yes, thank you. So here's, you'll have come over here because you'll have to do something with the computer here. I'm going to explain what I want you to do. So what you're going to do in a moment is make a maze. Now, don't relax, you don't have to do too much. Oh, by the way, what's your name?
My name's Lauren.
Lauren, okay. Lauren, what I need you to do is to make a maze, but all you have to do to make a maze is pick any square that you like and click on it. And as soon as you click on it, it's going to make a maze with, can you identify what's special about all the purple squares in there? I didn't say there was going to be a test, but can you, all the squares that are shaded in there, there's something that they all have in common. Those are all dead ends, right? Those are all the places that if you were walking around this maze and walked into one of those purple squares, the only thing you could do is turn around and come back out. And the place that I clicked, which was it right here? I think it was right there. The place that I clicked is one of those dead ends. But there's like 30 of them, right? And so what I want you to do is you decide where you want to click. Anywhere you like, again, click anywhere you like. It'll make a maze. That will be one of the dead ends. And this is important. Click on that spot, and then move the mouse off to the side so that I can't see. You don't leave it hovering over the place that you clicked, okay? So I'm going to step over here in the corner so I can't see what you're doing. In fact, I'll even step outside the room. Go ahead and tell me when you're ready. All right. So my job is to figure out where you clicked, what you were thinking of. Maybe, you know, if I'm going to read your mind. Obviously not really. But I'm going to figure out where you started this whole process of making this maze, where you clicked to begin things. And I have to look a little bit here because this is an extraordinarily large maze. Where are you from, Lauren? This might help me a little bit.
From Glandor.
From Glandor. So kind of right up here in sort of north. yeah, in this general area, but northwest Ohio, right? So I kind of sense that you didn't want to be in the northwest part of this maze, but you did like the north. I kind of think that you were up in the northeast part of the maze. I'm going to take a shot here. That was your starting point, right? Yeah, that was the starting point, right? Oh, and there's something else that's going on here that we'll talk a little bit more about later, but yeah, that was where the place that you started. Out of all those dead ends, that was the right one, and it played me a little fanfare right there. I also sense that you want to go sit down now, so please go ahead. Okay. So this is the only magic trick that I have personally developed, and the only one I'll probably ever get reasonably good at. I do this for like middle school students, and they're just absolutely awestruck by my ability to read minds. And I'm going to show you how this works. Okay, I'm going to tell you how this works, but I'm going to make you wait till the end of the talk to find out how this works. But I'll just show you. I actually want to try something, because when I do this with like middle school students, I will sometimes, just out of curiosity, see. I'm going to do this a couple more times, and then I'm going to see if anybody out there has any inkling about where to start. So this time the computer picked where the starting point was. And I will find the starting point and show it to you. But if you already want to start trying to formulate a guess, you can do it. The starting point for this maze is right there. Okay? And I'll do this a couple more times. So here's another one where, again, the computer picked that starting point, decided where to begin the whole process. And this particular maze started right there. And I'm not giving an awful lot of time to process this. I'll do it one more time. But then we'll see. Oh, and I should actually do this one more time just to prove that it's not programmed to like play that fanfare no matter where I click. If I get it wrong, it'll tell me I got it wrong. That was a wrong answer. And this is the wrong answer. And this is the wrong answer. And the right answer in this case is, ooh, can I find it? It's right there. Okay, so I'm not going to ask you, especially at this time of the afternoon, to like put any money down. But does anybody want to hazard a guess of all the squares that are up there about which one might be that one that I'm picking out from this maze? You have almost no information except for having watched me do this like 5 times. Anybody want to hazard a guess? There's usually in middle school, there's like some kid at the back of the class who raises his hand, and if he's right, everybody's like really impressed. So you could have a chance to really impress your classmates if you get it right. Anybody want to take a stab? Faculty, you can try too. You want to go ahead? All the way over on the right. The second one, this one right here? That one? Well, that was a valiant effort, but yeah, you were brave enough to try. We ought to give you credit for that. Anybody else want to? I see some people pointing at something over there. What do you think?
Bottom right corner.
Bottom right corner. This one right here? Oh, that's strike 2. Yeah, what do you think? It's hard to describe, right? The one on the right, this one right here? No, that's not it either. Well, shall we try one more guess? Anybody want to try one more guess? I mean, I should say, these are particularly bright middle school students that I work with, so you shouldn't feel bad about this at all. And anybody else want to hazard a guess on this? Everybody's having heard 3 strikes here. You don't necessarily want to go. I'll just tell you, it's this one right here. It's that one right there. So that's mystery number 1. That's mystery number 1. Okay? I got my volunteer from the audience. Mystery number 1 is my mind reading trick. And I'll just say, if you want to play around with this on your own, after I tell you how this works, you might want to play around with this and impress your friends with your mind reading abilities. That's the address. I'll repeat that at the end if you don't have something to write it down right now. And I will explain this particular approach later. Okay? It seems like magic until you see what the answer is. So here's mystery number 2. I called it marbles solely because I needed a word that started with the letter M. The original source of this was a paper called Playing Pool with Pi, which is equally fun to say, by a mathematician named Gregory Galperin, and I should have checked to see how he pronounces his name. I think he was at Southern Illinois University. But he published this in 2003 in something like the Journal of Mathematical Dynamics. I have a citation for this at the end if you want to read this, and I actually would highly encourage you, if you're interested in math, to read this paper. It's really accessible, fairly easy to read. But he described this experiment where two marbles, he used billiard balls, I'm using marbles, collide with each other in a wall. So you can see an illustration down below. That illustration is from his paper. And we've got a small little marble with a mass of m, and a larger marble with obviously a larger mass that is traveling toward it at some velocity. They collide with each other and bounce off of each other and bounce off the wall that is off on the left side of the image there. And when they have these, I'm sorry, let's see if I can adjust this just a little bit. When they bounce off of each other, they have these collisions and bounce back and forth, and they exchange energy in such a way that eventually the larger mass that was traveling this direction has received enough energy and momentum to travel back the other way faster than the first marble, so it gets away. So there is some finite number of collisions. And if we count the number of collisions, it turns out there is a really surprising connection to the number pi. And here specifically is how this works out. So we're going to make it simple. We're going to say that marble number 1, the smaller marble, has mass 1 rather than m. And I'll say that marble number 2 has mass m. Okay, so I'm changing the rules a little bit just simply because it's easier to have one mass just choose it to be 1 and the other one choose to be some multiple of that. And we're assuming here that all these collisions are perfectly elastic, which never really happens in nature. Anytime, if you hear two billiard balls hitting each other, the fact that you can hear them hitting each other means it's not perfectly elastic because some energy gets lost. Okay, but we're pretending there's perfectly elastic collisions. If you have two equal masses, and I thought about doing this also as like getting volunteers from the audience, but just imagine that there are two people up here. I'm one of them. There's another person right here. Equal masses. If I am traveling toward this thing and bump into this mass, this marble, what's going to happen in a perfectly elastic collision is I will stop dead. I will transfer all of my energy to that second marble, or actually I called it marble number 1, so I should say the first marble. It will continue down, bounce off the wall, come back and hit me. It will then stop dead in its tracks, and I will continue this way, and that will be the last collision. So 3 collisions, three total collisions in that case. Now here's where things get kind of weird. If the second mass, marble number 2, is 100 times as massive as marble number 1, it ends up, if you count the number of collisions, there's 31 of them. Nothing too extraordinary about that yet. 3 collisions and then 31. But if you go up to 10,000, a much bigger second marble than the first one, 10,000 times as massive as the first, there are 314 collisions, and it's starting to feel like this can't be a coincidence at this point. And it is in fact the case. You can prove that if you go up in successive powers of 100, 10 to the 2n, you get n plus 1 digits of pi. So the next one is 3,141. And after that, 31,415. Okay? So that sounds nuts. That does not sound like it could possibly have anything to do with pi. Just like I did my mind reading trick. It sounds kind of crazy, a little bit mysterious, a little bit weird. So how can we understand this? I'll just show you. This is not a proof. I'm going to go through something like a proof of this. But this is just an illustration, an animation that shows what those collisions look like. So this is 1 versus 100. And it's, again, not a proof because you have to take my word that I simulated this correctly when I created the animation. But there's 1 collision, 2 off the wall, 3 off that, and there's 29, 30. There is 1 more collision about to happen as mass number 1 chases mass marble number 2 and bounces off. And they're both still traveling this direction, but marble number 1 can no longer catch up to marble number 2. That was the last collision. Okay, I can't do there's no point in trying to do an illustration for 10,000 versus 1. 314 collisions, we just kind of have to assume that's going to be the right answer. But if you read, as I said, I recommend that you read this paper. At the end of his paper, he's telling the story about coming up with this observation. He had kind of explored this simple model of bouncing billiard balls, and he said, oops, hang on a second, there we go. When he first talked to that, the first time he presented this, he showed it to the audience and explained what was going to happen, and everybody was like, nah, that can't be right, until he explained, until he gave the proof, and then they looked at the proof and said, oh, okay, well, yeah, that makes sense. Okay, and he said that happens a lot. And I will say, I stumbled across this for the first time almost exactly 2 years ago, this particular piece of information, because we have a Pi Day celebration at Bluffton every year. And 2 years ago, we had a kind of a plan for what we're going to do on Pi Day, and I thought, oh, let's just see if there's any other really kind of weird things about pi. And I literally Googled weird things about pi, and I came across a guy who blogged about this result and described it, and I looked at it and I said, nah, that can't be right. Until I looked at this guy's paper and saw his explanation as to why, and so I had the same kind of result. Now, in Galpern's paper, if you read it, he has a particular way of proving that looks at the positions of the marbles. I'm going to go through briefly, not in too much detail, a proof of that only talks about the velocities of the two marbles. There's going to be a little bit of math here. I don't know, I did not ask like what kinds of math classes you're in, or if you've had physics classes that are kind of helpful for this too. But my point is to kind of convey the flavor of this proof without going to all of the details. I'll show you some variables, but I'm not going to actually talk about solving equations. So we're going to start with a couple assumptions that marble number 1 has initial velocity 0. It's just sitting there minding its own business. Marble number 2, we're going to say that velocity is -1. Negative because it's moving in that direction. So negative direction, positive direction, negative velocity, positive velocity. And when we say the collisions are perfectly elastic, I said something about this before, but we need to spell out mathematically, physically, what does that mean? It means that when they collide, when the two marbles hit each other, both momentum and kinetic energy are conserved. They stay the same. Down at the bottom, those are the formulas for momentum and kinetic energy. I'm not going to go into too much detail about that. If you've had a physics course, you might have seen those two formulas for momentum and kinetic energy. But we need to have these things at least lurking in the background in order to understand what's about to happen here. And specifically, when we say the kinetic energy and momentum are both conserved or stay the same, we mean that we can change the velocities of the two marbles, and we saw that happen in the animation, right? The marbles were traveling at different speeds as they collided. We can change the velocities, but we have to change them in a way that those two things remain constant. So the momentum and the kinetic energy just before the collision has to be the same as the momentum and kinetic energy after the collision. Okay, and it notes there, this comes down to solving a system of 2 equations and 2 unknowns. That's our system of equations right there. So those of you that remember that stuff from, this is an Algebra 2 topic, but this is solving a system of equations, right? We won't do the algebra, but we'll kind of dance around the algebra a little bit. Now, the other kind of collision we have is when marble number 1 bounces off the wall, and remember, it's the only thing that can bounce off the wall. Marble number 2 is never going to make it over the wall. But when marble number 1 bounces off the wall, perfectly elastic means it just heads back in exactly the opposite direction, which means its velocity changes from negative to positive. When it's heading this direction, when it's heading this direction, the velocity is negative, hits the wall, bounces off, so now its velocity is positive, and it's exactly the opposite of what it was before. If it's going this way at 0.3, negative 0.3, it'll come back this way at positive 0.3. And notice the kinetic energy will stay the same in that situation because we're squaring the velocities, so positive or negative doesn't make any difference. But the momentum is going to change. The net momentum in the system will change because one velocity, v1, changed from a negative number to a positive number, so when we plug those velocities into the momentum formula, we have more momentum every time we hit the wall. But the only time the momentum changes is on the times that we hit the wall. Now, we need to have some way of visualizing this. I said we wanted to skip the algebra. This is how we're going to skip the algebra. Algebra is a great way to communicate mathematically and to do things mathematically, but it is deadly boring to watch someone solving algebra problems. I apologize to anybody who likes watching someone solve algebra problems, but we're not going to solve algebra problems here. Okay? So we're instead going to look at we're going to go to another great system for solving math problems, which is to look at pictures. And we're going to go with graphing on the horizontal axis the velocity of marble number 1, and on the vertical axis the velocity of marble number 2. And when we say there's perfectly elastic collisions, I just have to, before I show you this next little bit, say that I just lied to you just now. Because actually what we're graphing on the horizontal and vertical axis is a slightly rescaled velocity. Because we've got different masses, mass 1 for marble number 1 and mass m for marble number 2, we're going to rescale the velocity for both those things in a way that I'm not going to go into. But it still boils down to what you can see in this picture. The 4 quadrants of our set of axes here. If we're in the first quadrant, which is, let's see if I can remember how to push there we go. The first quadrant up there, both V1 and V2 are positive, which means they're both moving in this direction. That was what we saw at the very end of those 31 collisions. Both marbles were moving, well, yeah, I have to change my order, but when we saw the animation, both marbles were moving this way, okay? If we're down here in this quadrant, marble number 1 is moving to the right, marble number 2 is moving to the left, and so on, okay? The same thing that we get with usual quadrants when we set up a coordinate system like this. Because kinetic energy is conserved, V1 and V2 have to fall in that circle. Again, the asterisk there is because I rescaled things, because I wanted to rescale the velocities in such a way that we're talking about a circle. Okay, and if you remember what that formula for kinetic energy looked like, it's got the square of V1 and the square of V2 in it. And if you think about the equation for a circle centered at the origin, it's x squared plus y squared equals r squared. So with the rescaling, this kinetic energy formula is essentially the equation of a circle. Without the rescaling, it's an ellipse. It just gets a little bit messier, so I want to make it into a circle. It has to fall in that circle. It also, there we go, V1 and V2 also have to fall on a line, and that line comes from keeping the momentum the same. Okay, so this is just a way of visualizing those two equations. I said we're going to forego the algebra. What we're really doing is taking the algebra problem and turning it into a picture. Okay, so we need to figure out, okay, now that we've got a way to visualize what the velocities look like, how does that help us to understand how many different collisions are going to be? So remember, I said we were starting with marble number 1 not moving, so velocity is 0. Marble number 2, the velocity is -1. Which means we're starting down here at the south end of the circle, because that is where V1 equals 0 and V2 equals -1. This is a unit circle, by the way, we've rescaled things. So this is where we start. And remember, in order to maintain kinetic energy, we always have to be somewhere in the circle. That's just where we begin on the circle. The first time those things collide, what's going to happen is we're moving along a line that goes through that point, the place we started with, and intersects the circle in a second place. I said before there's an algebra thing we have to do is solving a system of equations, and what it boils down to is if we are currently right there, when the collision occurs, we have to move to another solution of that same system. The intersection of a line and a circle, I mean, in this case, this line and circle intersect in two places. We started before the collision. We were down here. After the collision, we moved to the one other point on that circle that has the same momentum. So that first marble to marble collision means we move, oops, I guess I advanced, which is fine. Means we move from the bottom corner to the into the quadrant number 3. Then marble number 1 is going to hit the wall, and when that happens, the velocity becomes the opposite. And when the velocity becomes the opposite, we move from V1 is a negative number. It's moving to the left toward the wall, and then it bounces off and goes over to the right side because the velocity is exactly the opposite of what it was before. It used to be moving toward the wall, now it's moving away from the wall with exactly the same speed. The opposite velocity from what it had before. Okay? And what happens next? Well, now marble number 1 is moving away from the wall. Marble number 2 is still moving toward the wall. They will collide again. And it has to be, again, the second solution to where that line crosses the circle. So we're going to end up over here. And then they're going to collide again. Oh, then marble number 1 is going to hit the wall again. And then they're going to collide again, and marble number will hit the wall. And at some point, we'll get up to that place right there where if we try to extend this and go further the same kind of way, there isn't a line through this. Actually, there might be a line that goes through that point, but ends up down here. At that particular point, marble number 2 is moving faster with a greater positive velocity than marble number 1. You see why? Remember, this is velocity number 1. This is velocity number 2. Marble number 2 is moving away from the wall faster than marble number 1 is moving away from the wall, which means that was the last collision. Okay, so this is just a way to visualize what those collisions look like, and means that we don't have to literally like make that animation that showed the 31 different things we had before. We can just draw a circle and then draw the lines and make this little zigzag graph, and that tells us what the collisions look like. This happens to be when m equals 4. Remember, mass number 1, or marble number 1 has a mass of 1, mass number 2 has a mass of m. If m is 100, we would get 31 collisions. When m equals 4, we get 6. Right? You see all those collisions? The first collision was when we transitioned from here to there. That was 1, 2, 3, 4, 5, 6. That was the last collision. Okay? Now, why do we get digits of pi? So this is my sketch of a proof. Remember, I kind of guided you through how to visualize this. I'm going to finish up this sketch, but I'm going to leave out an awful lot of detail because the rest of it, I mean, there's some algebra we could do along the way. There's a little bit of geometry we need as well, but the main observation we want to make is each one of those little zigzags, and by zigzag I simply mean, come on, starting from here, going up diagonally and going straight across. So that's one zigzag. And starting from here, going up diagonally and straight across, up diagonally, straight across. That's what I'm calling a zigzag. Each zigzag represents 2 collisions. The diagonal transition up is when the 2 marbles collide. The straight line across, the horizontal line across, that's when the marble number 1 hits the wall. And this is the geometry part. Each one of those zigzags subtends or captures an arc on the right side of the circle. So what I'm referring to when I say subtends an arc, that's an arc, a piece of the circle. And this zigzag right here captures or subtends that particular arc. This is what's called an inscribed angle, okay? It's a geometry idea that you may or may not have even learned about. The important thing that turns out to be the case is every one of those arcs that you see is the same size and have to be the same size because geometry tells us when we do that, all those arcs are the same size. So how many arcs can we fit along there? That's really the question, because zigzags correspond to collisions, arcs correspond to zigzags, so how many arcs are there? Well, now I have to fill in a little bit more detail, but again, not going to go into all the detail for this. Each one of those diagonal lines has a slope of -1 over radical m. You're just going to have to take my word for it, because I never even told you how I rescaled things, but trust me, that's the slope of each of those lines. The greater the mass of marble number 2, the shallower those lines are going to be. The greater the mass, the greater the value of m, the shallower those lines will be because the slope will be closer to 0. So the angle that you see in each of those inscribed angles is the inverse tangent of 1 over radical m. And if you're starting to glaze over because you weren't expecting inverse trig functions in this, don't worry, we're not going to do too much with that. Just go with it, okay? So if we have a mass which is 10 to the power 2n, a power of 100, in other words, 1, 100, 10,000, 1 million, and so on, it turns out the inverse tangent function is such that it has a linearization that close to 0, the inverse tangent of x is close to x. So theta is pretty close to, so theta in this case is pretty close to 1 over the square root of 10 to the 2n power, which is, say, 10 to the negative nth power. The arcs themselves have a measure which is twice as big as that. Again, a little bit of geometry there that I'm not going to stress you over. That's a geometry piece of information that the arc measures are twice the inscribed angle measures, which means there's room for that many arcs. Pi over 2 times 10 to the n, and remember every arc is 2 collisions, so that means roughly pi times 10 to the nth power. 3, 31, 314, 3,141, and so on. Now, this proof is not exactly the same as Galperin's proof, okay? Like I said, I won't pretend, I'm not even going to ask for a show of hands if you all had the same reaction as his audience when he explained the proof, and everybody's like, oh yeah, that's obvious. I don't think that's probably the case, because I'm not even sure it was the case when he did it, if I'm being honest. But with a little bit of thought, you can process this. This is an approachable problem, and we can find out in the end, oh, sure, okay, 3, 31, 314, etc. There is a way that you can make sense of that, and kind of the key is just thinking about that picture right there. Okay, back to mystery number 1, which I hope you still have enough, first of all, energy to pay attention to me for about 20 more minutes, but also enough curiosity about the mind reading trick, because I'm going to show you how it works. In order to do that, I have to, first of all, show you how that maze got made. I mean, I just said, come up here, click anywhere on this, and bam, it's going to make a maze. And we didn't really talk about what algorithm, what process was used to make that maze. So this is, the first page you saw, that was mine. Okay, I created that page, probably about 10 or 15 years ago now. This is a little bit older even. When I teach our introductory programming class at Bluffton, one of the things I like to do is just to get students in the mode of thinking about how you solve a problem. Writing a computer program is about describing a process for solving a problem. And I think that making mazes is a reasonably approachable kind of thing. So this page is a little older. And let me jump over here. Making mazes, there we go. So I'm going to show you what the process looked like to make this maze. I'm going to start by saying there are literally dozens of ways that you can make mazes. Okay, I'm going to show you one of them, maybe a second one briefly, but I'm only going to go into detail about this method that's called a random walk or a depth first search approach to making a maze. And this page, unlike the other one where you click and bam, you make yourself a maze, this page right here is designed to show you step by step what the process looks like to make this maze. The full description of what we're about to do is up there in the top center of the web page. That is the entire description of what we are about to do to make this maze. Okay, now I have to define a couple terms because some of what's up there doesn't make sense until I tell you what the words mean. But we're going to make a maze in this grid down here. Where the purple square is what I'm calling the starting point, and it may help you to visualize that this is like a great big warehouse with a bunch of individual rooms, and we've torn the roof off, and we're looking at it from up above, and there's a guy with a sledgehammer standing in one of those rooms. And his job is to start knocking down walls and turn this thing into a maze. Okay? And so here's what he's going to do. Choose a starting cell. We've already done that, right? Choose a starting cell. Question number 2 is where we're going to spend most of our time going through this process. Does this cell have at least one available neighbor? What that means is, from the point of view of the guy with the sledgehammer, where he is right now, an available neighbor is a neighboring room, a room either north, south, east, or west of his current location that has never been visited before. That's an available neighbor. So what's the answer to that question? Yeah, there's 4 available neighbors. There's 4 different ways you can go. And so if the answer is yes, if there's even one available neighbor, he randomly chooses a direction among those available choices and moves into that room. So he is going to, when I click take next step, he is going to either go north, south, east, or west. I have no idea which direction he's going to go. Happen to decide to go south. And so he knocks down the wall, walks into that new room, and then goes back and asks the same question again. Is there an available neighbor from where I'm right now? North is not available because he has been there before. Okay? But there are 3 available directions. You go east, west, or south. So the answer once again is yes, there's an available direction. And he happened to choose to go south. And then he went west. And I'm just going to let him wander around here. This is why it's called a simple random walk. He is literally randomly walking around this building, knocking down walls. And it doesn't really get interesting until we finally get to a place where the answer to that question in number 2 is no. So far, he's always had at least one available neighbor. But eventually, he will box himself in. Oh, so close. Eventually he'll hit a place where, oh, come on. This is taking an incredibly long and awkward time. Okay, so he's inevitably going to box himself in here somewhere. Can you see that? If we follow the set of rules that we've got now, he has to, at some point, find himself backed into a corner right there. Okay, this is the very first time in this whole stretch that he's got nowhere else to go. Right? He doesn't have an available neighbor. So now we're finally going to look at the no branch of question number 2. When he finds himself in a place where there's no available neighbors, this is when he's going to backtrack. He's been laying out this trail of breadcrumbs behind him. He's going to take a step back into a place he has been before, but he doesn't have to knock a wall down to get there because he's already knocked that wall down. So the next step is he's going to go north. Now we're still asking the question number 2. What's the answer to question number 2 now? Well, once again, it's yes. I mean, there is one place there's one available neighbor from where he is. He is going to definitely go west. And now he's once again in a corner, and he's going to back up. And the answer is still no at this point. There's no available neighbors, so we'll back up again. Now the answer is yes. He will definitely go east. And then he has to back up, 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 back up. Finally, he has, again, an option as to what's going to happen next. Right? And let me go ahead and take those next steps and just ask, what's the next actual progress we're going to make toward making a maze? Where's the next wall we're going to knock down? Can you see it? The next wall that we're going to knock down? It's this wall right here. Definitely the south wall of that cell. Do you see why? The rules that we're following here say the next steps he's going to do 3 backtracks. Take 3 steps back. I apologize to the camera in the back that I'm moving around all the left and right all again and again. He's going to take 3 steps back. Now he has to go north because anytime the answer to that question in number 2 is yes, he has to choose among them. He has to go north. And what's the next wall he's going to knock down? It's going to be this one right here, right? Because that's the next time he's going to find himself in a room where there's an available neighbor. Okay, so definitely going to go north. And once he does that, he's broken into a whole new area where there's lots of places he can go. I'm going to go ahead and have this thing carry out the rest of this by itself. Okay, but it's doing exactly the same thing over and over again, making the same set of decisions just based on primarily question number 2 and deciding what the appropriate action is based on question number 2. At the end of this process, with absolute certainty, I want to say there's 2 things we want to have in a maze. We want every part of the maze to be connected. If I tell you start in the upper left and go down, the upper right and go down to the upper left, no, this is the upper left for you. Start in the upper left, go down to the lower right, there is definitely a path that you can get between those 2 locations. Because everything about this maze was done by this one guy walking around the rooms in this warehouse, knocking down walls. There has to be a way from here to there, or indeed any 2 places you pick in this maze. Let's see, he has a few more things to knock down. He's got to knock down that wall, this wall next, and then this wall. And next he'll knock down this wall when he finally backtracks at this point. Then he's got to carve out everything that goes on over here. And after that, he's just got one more wall to knock down right there. And he's basically done, but we'll let him go back to his starting point. Okay? When Lauren clicked on the maze before, that's what was happening behind the scenes, except it all happened instantaneously. Okay? Now, if you look at this maze, there are quite a few dead ends in this maze, right? They're not colored in, but let me just kind of point them out. One dead end is the place where the whole thing started, which was right there. Right? That was the place that started. But there's a dead end right next to it, and there's a dead end right there, and a dead end right there. Dead ends are pretty easy to identify because they're rooms that have 3 of the initial 4 walls still intact. If a room still has 3 walls intact, it's a dead end. You walk into that room, the only choice you have is to turn around and go out. Statistically, this is way beyond what I have time to talk about today, but statistically, it turns out that this approach to making mazes gives you about 10% dead ends. Something in the neighborhood of 10% of any maze that you make, ballpark, will be dead ends, right? I mean, it's literally going to be like a binomial distribution, et cetera, but roughly 10%. So this maze is 260. There's about 25, 26 dead ends in there if you want to go through and count them all. Okay? That's how this maze got made. Okay? Now, just a couple observations before I jump back to the other page where I was doing the mind reading trick. Okay? If you remember, it took me an awful long time till he finally got boxed in and had to start backtracking. Okay? That's pretty typical. If you use this approach to making a maze, and again, there's dozens of ways to do it. This is arguably the simplest one to describe. But at the beginning, it took a very long time until he finally had to start backtracking, which kind of, you could roughly summarize as saying that at the start of this process, he has many more free choices available to him to decide which direction he's going to go. We got to a point where we said, well, now we know what he's going to do next. He's got to knock down that wall, and he's got to knock down that wall, because he's going to backtrack, and we can see exactly where he's going to end up. But at the beginning, we had a lot less clarity about what was going to happen next. It was always taking random steps, left or right, up, down, and so on. So we tend to have more freedom at the beginning of this process. So let me jump back over here again. And I'm going to make a smaller version of this. Now that you have seen this, there's 7 dead ends in this maze. And let's just name them 1, 2, 3, 4, 5, 6, 7. Okay? And fun fact, the way I named those things, you might have thought down here I'd go 6, 7, but I went 6, 7. I named them bastrophodontically. If you want to impress your friends with a big, long word, bastrophodontically means as the ox turns. So if you imagine that you were like you have an ox pulling a plow here, the ox would go this direction, 1, 2, then turn and come back this way, 3, 4, 5, 6, 7, and then, going along this row, then going along this row, and then coming back this direction. So that's why 6 and 7 were that way. I learned that word almost by accident at a math conference like 20 years ago. It's one of my favorite words, bastrophodontically. So, 1, 2, 3, 4, 5, 6, 7. Anybody want to venture a guess now that you know how this maze got made? Yeah, what do you think?
Very right side, the second one down.
Oh, you're not even using my numbers, but okay. The second one down, that would be what I called number 3 or 4. I don't even know what I called it right now. But you mean this one, right?
Yeah.
Okay. Can you give me any idea why you picked that one? Before I click on it, we find out if you're right or wrong?
I think it just makes the most sense, like, just logically, if you picked any of the ones in the middle.
It felt right. So I will say, when I learned this little trick that I've been showing you, my initial way of doing the trick was, I kind of think it's that one. And it took me a long time to figure out what it was. And guess what? That's the right answer. Because it kind of felt right. But can we figure out why it felt right? And again, that's a little bit of a hint right there, what you're seeing. And I'll talk a little bit more about that. But let's try this experiment one more time. Only 6 dead ends this time. Anybody want to say what they think this time? This one's a little bit, I don't know if I'd call it necessarily trickier. There's only 6 of them, but you might be drawn to some wrong things. You still don't have an awful lot to go on. Anybody have a guess? What do you think? The center on the, so like this one? Oh, this one right here. So basically the same place we were before. Man, what are the odds of that being right? Yeah, it was that one. Okay. Anybody else want to try their luck at this? There's, again, only 6 of them here. It's not this one over here. I'll tell you that right now in case you're thinking it's always on the right side. No, it's not that one. This is wrong. That's not it. So I've eliminated one of the wrong answers. Anybody want to guess on this one? I see some people thinking about it, but nobody seems inclined to raise your hand. I'll just tell you, it's this one right here. Okay? And let me pause on that right there. What is significant about that blue path? I've shown you that blue path and said this is kind of important, but I haven't told you what it is. Can you see what is significant about that blue path?
It's like the start out path, just let's reach the first dead end.
Yeah, so when we talked about the process to make this, if the guy started there, if that's where the guy, and it turns out that is where the guy with the sledgehammer started, We know that he had to go south and then east, 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 south, east, north, north, east, north, west, north, north. We don't know what happened next. So the end of that path, up there in the top row, that last blue square in the top row, is the first place. We don't know what he did next. He might have gone east, he might have gone west. Okay? I call that the corridor that leads away from that dead end. Every dead end has a corridor, right? Here's a corridor for this one right here. If he had started in that place, the end of that corridor is the first place that he would have a choice as to whether he went east or west. I mean, if the guy with the sledgehammer started there, he had to go east and south, but then we don't know what happened next. And the corridor away from here is just one step, because he had to go west to begin with, but then we don't know whether he was north or west after that, because there's 2 walls knocked down from that particular place. So there's something, back to the PowerPoint here. So the observation is every maze, and by the way, not just mazes made by the way we're talking about here, not the simple random walk mazes, but any kind of maze. If you look at a dead end, it's always got a corresponding corridor, which is the sequence of cells that leads away until you first have a choice to make as you go away from that particular dead end. And here are 4 mazes, or sorry, this is a maze, a single maze, 4 copies of a single maze I made earlier, and it had 4 dead ends in it. And those are the corridors that lead away from those 4 dead ends. Okay? So we can kind of see, for example, this corridor ends right there, because once we get to this point, we don't know whether we're going to go this way or that way. Corridor for this dead end right here zigzags all the way around until we get down to the south end of the maze, and then we don't know whether we went left or right. This corridor is just one step, because once we take that one step north, we don't know whether the next step was east or west. This corridor right here ends right there, because again, don't know if we went north or west from there. Looking at those 4 dead ends, do you have a guess as to which one of those dead ends was the starting point? I can't get a fanfare for it, because this is just a screenshot, but which of those 4 dead ends do you think? Number 2? I see somebody indicating number 2. Why'd you pick number 2? It's long, and that is an important thing to say that I kind of alluded to before. At the beginning of this process, the guy has the most random choices to make. The longer it goes on, the less freedom he has to make moves. And it does happen that a lot of times, the longest corridor is the starting point. Now, there's something else. That is, in fact, the right answer, so I'll, ta-da, that's your little fanfare for getting the right answer. There's something else. Aside from that, the fact that that corridor is really long, look at the rest of the maze, apart from the corridor in each one of these things. There's something significant about the rest of the maze in this case, when you look at the corridor there, versus the rest of the maze in these other cases. Can you identify what is significantly different about the right answer and what the corridor does to the rest of the maze in the right answer versus what the corridor does in the other answers, which are all wrong? What'd you say? It cuts it into 2 pieces. The right answer, this one right here, once we get to the end of that maze, if you kind of erase, mentally ignore all the blue stuff, there is a bit of the maze over here and a bit of the maze over here. It's completely separated into 2 pieces. None of the other corridors do that. And that's what you're actually looking for. The way you find the answer is you find the corridor that divides the maze up into 2 distinct pieces. And it will only, I'll say this and then I'll explain why it's not entirely true. It will only happen if you have located the corridor that starts at the initial point, the place where the guy started the whole sledgehammer process. The only exception to that is if you end up with a maze that only has 2 dead ends in it, which is possible but very unlikely, if you only have 2 dead ends, there's no way to make the decision. You cannot decide. But yeah, in this case, that's what it is. And really importantly here, this doesn't just work for, I was making mazes on a square grid. It works on any kind of grid. Can you figure out where it is there? It's a little harder to train your mind to follow the corridors, but can you identify the right answer for this one? If you can kind of wind around a little bit, I mean, there, for example, is the corridor from the first one right there, right? From that dead end right there, that's the corridor, that's where it ends, because here's the first place you have a choice to make. That does not divide the maze up into two separate pieces, right? But this one does. That corridor, which is the longest, again, divides the maze up into two separate pieces. That was the place that maze started. Guaranteed. Now, I'm going to really get sketchy on the proof here, partly because we're running out of time, but also because it is just really hard to translate this into good language for proving things. But when we make a maze with the simple random walk method, this is the kind of thing you want to keep in mind. If we are in the process of making the maze, and by the way, the purple cell is where the guy currently is. That sledgehammer guy is currently there. He started at the other end over there in like row 3, column 4. If we're right there, if we're in cell C, and we step into a contiguous region, meaning a connected bunch of cells, the rest of the maze at this point is a single contiguous region, then the rule is, and this is a consequence of that very simple step-by-step description, we cannot backtrack into cell C. We will eventually find our way back into cell C, but we cannot get there until R, that contiguous region, which is, say, every other place in the maze, is finished. We have to visit every place in R before we can go back into C. That's what the rule says. So we can say with absolute certainty, doesn't matter what he does next, this is not the end of this corridor, right? Because if he happens to go north, he's not going to backtrack into that cell until the rest of the maze is finished. He's not going to backtrack into that cell until the rest of the maze is finished. He's not going to backtrack into that cell until the rest of the maze is finished. And if he doesn't backtrack into that cell until the rest of the maze is finished, he can't knock down any more walls in that cell. That cell will always have 2 intact walls. He knocks down one wall going in, one wall going out, but there'll be 2 walls left over behind that he will never knock down. In fact, that's the first place where, first of all, at this point he has 2 choices, he go east or west. But if he goes west into that lonely cell right there, he is definitely going to backtrack right away without finishing the entire maze. If he goes right into that cell, he will knock down all of these walls over here and then backtrack to here, and then he'll go west. And that's the first place that's going to happen. That is the end of the corridor from this starting point. Zigzag, 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 right? That's the end of the corridor right there. And we can use, again, that's a very rough sketch. But what it boils down to then is, if C is next to 2 separate contiguous regions, if the cell we are currently in has separated the maze into 2 separate regions, which was the observation we made before, there will be paths out of C into each region, by which I mean from, where am I? I've lost maybe I don't have oh, there it is, there's the laser. There'll be a path out of the cell into this region, that's one part of it, and into this region, and that's the only time that can ever happen. It can only happen from our initial starting point. I think that's my last slide. Yep, that's my last slide. So, if you have any interest in exploring any of this further, the first 3 QR codes up there and the first 3 links up there, the first one is for Playing Pool with Pi, the original paper by Gregory Galperin. Okay, again, very much encourage you to read it. 3 Blue 1 Brown has a video channel. I don't know if any of you have ever watched 3 Blue 1 Brown. It is math talks. He has a talk about that particular problem where he presents, in the video following the one that I linked to there, he presents a proof that's an awful lot like the one that I came up with. I will say I didn't look at his proof before I did mine, so we kind of came up with it independently. I gave a talk at Miami University a year and a half ago where I talked about this pool problem and actually extended this. So what if there's like 3 balls or 4 balls, and I wrote some Python code to simulate that sort of thing. That's how I came up with that little animation for the 101, the 2 balls. And so if you want to go and see my Python code, it's nothing real fancy, but that code would take you to my GitHub page. And this, as promised, is the short version of the link to my puzzle page now that you know how, at least even if you don't understand all the math and don't understand the proof, we talked about enough of it that you could tackle that problem and then amaze your friends, or maybe, if they're really gullible, bet them money that you can figure out where they started and make some money off them before they finally realize that you have some kind of trick up your sleeve. And I think that does it, because that's pretty much the end of my slideshow, right? Yep, that was indeed the end of my slideshow. Thank you very much, and gotcha, to 1:55 here. Are there any questions anybody would like to ask? You're welcome to come up and talk to me afterwards, but any questions you want to throw out to make people stay in their seats for like another 30 seconds while I answer? If not, again, please feel free to come up and talk to me individually, but thank you for your attention, and have a good afternoon. Oh, if you are around next Friday, we at Bluffton, I know you guys are in spring break, but we at Bluffton will be doing our Pi Day at 3 o'clock on next Friday. So if you're around, you're more than welcome to join us. You'll get to hear me sing my prize-winning song about pi. So if that's any kind of incentive at all, and you get pi too, so that's probably more incentive. You too.
I need to